This is your friendly reminder that when we have vector-valued functions, there's two types of second derivatives we need to be thinking about, we need to know about. The first type is the one that looks like this. That certainly looks like a second derivative. The other type is ones that look like x double prime of t, comma y double prime of t. That also looks like a second derivative. They're used for totally different things. They come out to totally different things. Clearly they come out to totally different things because this is going to be a number and this is going to be a vector. So obviously they're different. What this one on the left is, this is the same as the derivative with respect to x of dy dx. In other words, this is the rate of change with respect to x of slope. This is the rate of change of slope. And we use this to answer questions about concavity. This purple one, on the other hand, this means something different. This purple one is, I'm going to write this in kind of a weird way, but I'm just trying to mirror what I wrote on the left side. This is the derivative with respect to t of x prime of t, comma, the derivative with respect to t of y prime of t. Even writing it, even with the warning that it's weird, looking at that's a really weird way. Ignore it if that looks nonsensical to you. This is how quickly your velocity is changing. The blue one is how quickly your slope's changing. The purple one is how quickly your velocity is changing. The word for rate of change of velocity, of course, being acceleration. We're going to use this to answer questions about acceleration. Now, you not only need to know when to use these, you need to know how to use these. So let's give that a shot. Let's say that I've got some vector-valued function. I've got some position of a particle where at time t, that particle is at cosine of t, comma, 2 sine of t. One question I could be asked about this particle is at a time t equals, let's say, pi over 3. I hope that comes out good. At time t equals pi over 3, is my particle's path concave up or concave down? I'm going to answer that by using the second derivative that has to do with concavity. I'm going to answer it using this second derivative, which I find this by keeping in my, I find this by doing the derivative with respect to t, my slope, over derivative with respect to t of x, and this I find by doing that process. Once I start it, it'll probably look super familiar to you. Let's see, I'll do this in green. dy dx, I find by doing dy dt over dx dt. The d over dt's kind of cancel if I want to think about it that way. And I end up with dy dt is going to be 2 cosine of t. Dx dt is just negative sine. And so I end up with negative 2 cotangent of t. And when I wrote this problem, I thought to myself, yeah, I'm going to make it a tangent one, not cotangent. No one likes to do cotangent, and I failed. It's cotangent. Oh well. Clearly I didn't plan this very well. I'm going to take this and plug it in over here, and I'm going to realize that my concavity second derivative is derivative with respect to t of negative 2 cotangent t over dx dt. I know dx dt is negative sine of t. So derivative of negative 2 cotangent of t, that's going to be negative 2 times negative cosecant squared t over, I'm going to keep it negative sine of t for now. Maybe I'll do some canceling of negatives and end up with negative 2 cosecant squared t over sine of t. And because I'm so eager to write trig in nice ways, cosecant is 1 over sine, so cosecant squared is 1 over sine squared. I'll combine with the sines already in the denominator to make negative 2 over sine cubed t. So to answer the question was about at time equals pi over 3, whether the path is concave up or concave down. All I have to do is plug in time equals pi over 3. If I plug that in, I get negative 2 over sine cubed pi over 3, which is going to come out to a thing. I don't really care about the exact number, but I do know that it's going to be a negative over a positive cubed. It's going to come out to be a negative number because this derivative came out to be negative. I know that I'm going to end up being concave down. That's that one derivative. With the same problem, the type of question they could ask, with the same particle at position cosine of t, 2 sine of t, they could ask at time t equals, we'll do pi over 3 again. What is the acceleration? To do that, I'm going to use my other version. I'm going to take the derivative of position to turn into velocity. Then I'm going to take derivative of velocity to turn into acceleration. Derivative of position is going to come out to be negative sine of t, comma 2 cosine of t. Acceleration is going to be negative cosine of t, comma negative 2 sine of t. Interesting to note that the acceleration is the exact opposite of the position. That's because this is kind of moving in a circle, so it's always being pulled toward the center, not actually a circle, a ellipse, a stretched oval, an ellipse. It's an ellipse. And if something's moving an ellipse, centripetal force, it's pulled toward the center. Anyway, that's my acceleration equation. So if I want to know acceleration at time pi over 3, I'm just going to plug that in. Negative cosine pi over 3, comma negative 2 sine pi over 3. That looks like it's going to be negative 1/2, comma negative root 3. Unless I made an embarrassing trig mistake. Hope I didn't. So my acceleration time equals pi over 3 is going to be negative 1/2, comma negative root 3.